Hey guys! In this lesson, we're going to learn about tension forces. That's the kind of force we see when we pull on a rope, for example. Alright, so let's get started. Suppose we've got a ball hanging from the ceiling by a rope. What is keeping the ball from falling to the floor anyways? After all, gravity is acting on the ball, right? Well, it's the rope that's keeping the ball up. So the rope must be applying a force on the ball to prevent it from falling. We call that force the tension force because the rope is being put under tension by the ball. So any force that appears as a result of pulling on a rope, a string, or anything similar to that is called tension. Actually, we can think of tension forces as being, in a limited sense, the opposite of normal forces. Resisting compression, they resist forces that cause things to stretch. For example, when we hang a ball on a rope, the rope applies a force to the ball which makes it resist being stretched out. The result is tension. Let's look at the ball on a rope again. If the ball has a mass of 10 kilograms, what is the tension force? How would we solve a question like that? Well, the answer would be 98.1 newtons upward. How did we get that answer? First of all, we have to look at the forces that are acting on the ball. One of them is obviously gravity. What other forces are there? Well, there's really only one other force, the force of tension. More specifically, it's the tension force being applied by the rope onto the ball. And since the ball isn't moving, the forces must cancel out.
Elastic force is the force exerted by materials that stretch easily when acted upon by another force. Some examples are the diving board, shooting a bow and arrow to push the arrow forward towards its target. Some of you someday may be crazy enough to go bungee jumping. These are all examples of elastic forces.
Tomorrow's lab is on elastic force. You're going to be using Hooke's law to perform a lab using a rubber band.
Hooke's law states that the force needed to stretch an elastic is proportionally related to the distance that it is stretched. For example, rubber bands, there is a proportional relationship between the force needed to stretch the rubber band and how far you stretch it. The greater the distance you stretch the rubber band, the greater the force needed to stretch. So a proportional relationship is one that both the independent and dependent variables grow together. When x gets big, y gets big.
Okay guys, so I am doing a little experiment for physics here, and it's about attraction and repulsion. So here I have is these two balloons, and what I did was rub this first balloon. This is attached to a thread in the ceiling. I taped to. I just rubbed the balloon on my hair to build out negative charges. I do the same to this. And like charges do not attract, so they repel each other. So this is what it does. I pull the balloon to the other balloon and it automatically pulls away. See that? I can just like jerk it to make the other balloon jerk without even touching it. But the purpose of the experiment is just to show that the attraction and repulsion of charges. So pretty basic, straightforward.
Hi guys, today I want to talk about equilibrium of forces. Equilibrium of forces. For forces to be in equilibrium, the sum of the forces acting on the object is zero. There is no resultant force. There is no net torque or no moment on the object either. no resultant force. The vector addition triangle will return back to its initial starting point when there is no resultant force. So we've got a force body diagram on the left, and then if I just add up the vectors, you can see we end up right back where we started with. That means that there's no resultant force. So free body diagram shows the forces acting on the body on the left, and then the vector addition triangle shows that there is no net force in this case. No resultant moment. Concurrent forces are forces whose line of action intersect at a single point. So the object on the left, the forces are all going through a single point, or the lines of action of the forces are all going through a single point. So this object will not rotate as the forces act at a single point. However, the object on the right, if we just draw where our lines of action are going through, you can actually see that for the three vectors, the three forces, the lines of action do not meet up at a single point, therefore there will be some kind of rotation. So this object will rotate as the forces are not concurrent. Ladder example, solved with concurrent forces in a vector diagram. So a uniform 6-meter ladder of weight 200 newtons leans against a wall at an angle of 60 degrees to the floor. What is the normal force acting against the wall? Okay, so it's 60 degrees, the ladder. Now, it's a uniform ladder, so the center of mass is going to be in the middle, and that's going to have a force of 200 newtons. That's the weight of the ladder. There's going to be a normal force acting on the ladder from the wall, and we don't know the value of that force, but we would like to find it out. And finally, there's going to be another force at the base of the ladder, and that's going to act not on the actual direction of the ladder, slightly up, and that, if you think about it, well, that's kind of opposing the frictional, it's part of the frictional force stopping the ladder from moving or from sliding downwards, but also acting against the weight as well. So it's got this kind of diagonal direction. Now the ladder is not moving, so that means that our forces must be concurrent. So if we look at the lines of action, we can see that they all meet up, okay, like this. Now if we do this to scale, what we can do is we can draw a diagram and we can find this angle here, which, if we look at a vector diagram, is this angle here. So if we draw this to scale and we measure it, and we actually find that it's about 74 degrees, well, now we can draw our vector diagram to scale, even though we don't know the normal force, but we know this angle here, and we know that the angle between the normal force and the 200 newtons is also 90 degrees, so we can solve this distance here, which is around 57.7 newtons.
The density is the sum of opposite degree opposite, and we have some example and definition of density, and we're going to show the example of the part of density, that is
This is the example we left at in the previous video. If we drop a piece of balsa wood and a metal pin of the same mass into the water, what will happen? Will both of them float, or will both of them sink? Or one stays afloat and one sinks? Just by intuition, we can say that the wooden block will float and the metal pin will sink. But if they're of the same mass, why does that happen? Shouldn't both float because of the buoyant force? This happens because of the difference in their densities. But what's density? Two forests? Which one is more dense with trees? Clearly, it's this one. So in the same given amount of space, if there are more things, we say that it's denser. Density is simply the measure of how compact the mass in a substance or object is. If we have to go by its scientific definition, we would say that it's mass per unit volume. In short, it tells us how much mass exists in a given volume. The unit of density is kilogram per meter cubed. Mass is in kilograms and volume in meter cubed. Coming back to our example, why did the wood float and the pin sink? The wood floated on water because the density of the wood is lesser than the density of water. Hence, the upthrust of water on the wood is greater than the weight of the wood. Hence, it floated. But the density of a metal pin is more than the density of water. Though it looks tiny, there's more mass per unit volume within it as compared to water. Hence, the upthrust of water on the pin is less than the weight of the pin. So what can we conclude? If the density of an object is lesser than the density of the liquid, then it will float. And if the density of an object is more than the density of the liquid, then it will sink.
Hello guys, thank you for watching our vlog about statics. That's all. So yun guys, please subscribe to my YouTube channel. Bye. Hello, my name is Hans B. Gonzalez and this is my group mate. Hi, Apple. Apple.